We were given a set of parametric equations, except for the equation we were given for the x direction is explicitly given, but the y is not. We do, however, have the derivative of the y component part here, and we could, if we wanted to, we could find an antiderivative for that and actually get y here. We don't necessarily need to. And I guess it depends on how complicated this is in terms of finding the antiderivative if we could find y. But either way, we're given the x component here, and we're given the y component. Remember, these parametric equations describe some curve in the coordinate plane. Okay, so keeping that in mind, when they ask us here for part A, what is the speed of the particle at time 3, okay, we ultimately need to figure out our velocity vector at 3. So remember, anything that's parametric can be written as a vector. We can take our two x's and our y's and we can write them as a vector, x of t, y of t. And if we can do that, then we can write the two velocities. We can write the velocity in the x direction and the velocity in the y direction. Okay? And we know that the speed is the absolute value of the velocity, and when we have something parametrically defined, the absolute value is the square root of the two squared added together. So ultimately our speed can be found by finding the velocity component in the x direction derivative. Okay, well, not the velocity's derivative. This is the velocity. So the x's derivative, if you will. And we already know y's derivative. That was given. So if we calculate that at time 3, if we put a 3 in there, we wind up with 4 plus 4 under there, which ultimately ends up with the square root of 8. Okay. So again, key issue here is that when we're trying to, if we have something that's either defined as a vector or defined in terms of parametrics, okay, the speed is always going to be found from the absolute value of the velocity. Okay? And the difference in this and an AB problem is that the velocity, okay, is just going to be one number. Okay? Because we're not dealing with a two-dimensional situation here. We're dealing with three variables. We have x and y in terms of a third variable, t, which ultimately makes the absolute value of the velocity equal to the square root of the two squared added together. So therefore we get radical 8, 2.828, and ultimately that was worth just 1 point only. So calculate the speed correctly. 1 point. Questions on that one? All right, total distance traveled on 0 to 4 seconds. Total distance traveled when we have a parametrically defined function or a vector function, either way. We know we find that with our arc length formula, which is ultimately that. We go from A to B, whatever the time frame is in this case, and square root of the derivative squared, and we integrate. And if we do that same thing with our same two derivatives we used in the last time, just dx dt and dy dt, I mean, that's just a straight formula. If we want to find total distance traveled and we have something that's defined with parametrics or defined as a vector, which is ultimately go hand in hand, then our distance traveled is always going to be our arc length formula, which is the integral from a to b of the square root of dx dt squared plus dy dt squared. And we calculate that. We get 2 points for that, 1 for having the integral right and 1 for having the answer right. Questions on part B? So again, I've told you for quite some time now, you need to start kind of making a catalog of things that you continue to get wrong. Okay? Because if you're getting arc length problems wrong when we have parametric equations, that's a category of stuff that you need to get some more practice on. We've got lots of problems in the book. I can find more problems for anywhere, but you need to kind of start cataloging which problems that you're having trouble with, which ones that you're getting wrong each time. And those are the ones we want to really focus on. Okay. All right, the part C of this, it says find the time when the line tangent to the graph of the particle is horizontal and is the direction of the motion of the particle toward the left or the right at this time. You have a reason for your answer. And ultimately, again, if we want to know when the path of the particle is horizontal, we ultimately want to know when the derivative is equal to 0. True? Remember, if we graphed x of t, y of t, if we graph that, we're going to get some kind of curve. It doesn't necessarily have to be a function, but it's some kind of curve. Okay, and if we want to know where the tangent lines to it would be horizontal, we need to know when the derivative would be equal to 0. Okay, and ultimately that is a matter of finding dy dx. Okay? And so dy dx, we know in parametrics is dy dt over dx dt. We know both derivatives. And so ultimately, okay, when is this going to equal 0? When the top equals 0. And this is a calculator problem here, so how much time am I going to spend on trying to do algebra to solve this? None. Okay, it's just a calculator problem. Put it in there and find out when it equals 0. It's 2.20794. So that would be the point where the derivative equals 0. And again, keep in mind the question was, find the time, okay, when this occurs. So ultimately, the time when it occurs is 2.2074. So if you found the derivative and set it equal to 0, that was worth 1 point. If you found the time, that's another point. Okay. All right. And then the third point was for the last part of the question, which was the direction of motion. It says again, is the direction of motion of the particle toward the left or right at that time? Well, ultimately, remember, our x and y's are the different components in terms of horizontal and vertical. So which one has to do with left and right? Dx dt or dy dt? Yeah, dx dt. Okay. So if we find dx dt at that point in question, our dx dt is 2t minus 4. And if we do 2t minus 4, we get something positive. Okay. So what does that tell us about motion in the x direction? The derivative in the x direction is positive at that point, so we'd be moving which way? Right, for you. Right. Okay. So ultimately, had they asked us the other question, what would the motion be like up and down? We would put that into dy dt, see if the derivative is positive or negative there. Okay. Questions? All right, and the last 3 points, we had 3 parts here to part D. It says there is a point with x coordinate 5 through which the particle passes twice. Find each of the following. The 2 values of t where that occurs. Well, ultimately, if we want to find the 2 times, and remember again it asks us to find the 2 values of t when the x coordinate is 5. Well, we have a nice equation for the x position at any point. So if we set that equal to 5 and solve it, turns out to be a nice factorable quadratic, because it's time 3 and time 1. So again, we get that because this is our x at any time, and we want to know where is x when time is 5. So we'll just solve that quadratic equation. We get 1 point for that. The part 2 of part D says the slopes of the lines tangent to the particle's path at that point. Okay, so this same point, which is time 1, these same points I should say, times 1 and times 3, we want to know the slopes of the lines tangent to the particle's path. So in other words, what's dy dx at time 1 and time 3? Well, we calculated dy dx up above. Okay. We know the dy dx is t over, or t e to the t minus 3 minus, t e to the t minus 3 all minus 1 over t to 2t minus 4, that is dy dx, and if we put a 1 in there we get 0.432, and if we put a 3 in there we get 1. So those are the slopes of the tangents to the curve at those 2 points, which was also worth 1 point. Questions on part 2 of part D? Alright, and the last part, we need to figure out the displacement. Read my crappy writing here. We running out of space. Should have just got a piece of paper. Huh? Ultimately, we want the y-coordinate of that point, given that y of 2 is equal to 3 plus 1 over e. So keeping in mind that if we want the y-coordinate of that point, where time is equal to either 1 or 3, still talking about times 1 and 3, if we want the y-coordinate at 3, remember what we're going to do is we're going to take the y-coordinate at 2, and we're going to add the displacement. Okay, so ultimately here, what is displacement? Displacement would be the area under the dy dt curve, wouldn't it? Okay, so if we integrate dy dt, I got a v, but it's actually a y there, sorry. So if we integrate from 2 to 3 of dy dt, that gives us our displacement. Okay, just like in AB problem, okay, we want displacement, we're going to integrate the velocity equation. The velocity equation for y is dy dt. Okay. And ultimately, if we do that, we're going to wind up with a final value of 4. If we do the integration here, again, keep in mind it's a calculator problem here, so we don't need to do the integration by parts that it would take to find the integral. So don't waste any time doing that. So bottom line here is if we calculate that, it turns out to be a total of 4. We also, if you if you do y of 1 and you do the integral from 2 to 1 of dy dt, turns out to be the same answer. It turns out to be 4 also. Okay. So at both of those points we get a position, or the y-coordinate of the point in question. Okay. Is we know the x-coordinate is 5. We were told that at the beginning. Okay. The y-coordinate in both cases is 4. All right. Questions on part 3? Last point, finding that 4 was with 1 also. Okay. Well, let's take a look down at number 6. Okay, number 6, we have an f function here. It's a piecewise function. We have g that's defined by an integral. So let's see if we can make some sense out of this problem here. The first part here is to write the first 3 non-zero terms and the general term of the Taylor series for cosine x about x equals 0. So we know that to develop any Taylor series, in this case it's actually a Maclaurin series because it's x equals 0, but ultimately that's the same thing in this case. We know that our coefficients are going to come from the derivatives. So if we find some derivatives here, we know we need to come up with the first 3 non-zero terms. And knowing that sine is going to be 0 means that these 2 terms are going to be out of there. So ultimately we wind up with 1 here, negative 1 here, and that again, remember, is just the coefficient of the term. The term is x squared over 2 factorial. This is x to the 4th over 4 factorial. And so the first 4 non-zero terms will be this. The key is in this general term, gotta make sure that we understand how to get these general terms here, because this is worth a point. Ultimately, you got 1 for that. Okay? And yeah, just 1 for that whole thing. Actually, it's 1 for this whole thing. So not even 1 for that. You have to get the general term too. Bottom line here is that we can see that it's alternating. Anytime it's alternating, we're going to need some negative 1 to some power. Okay, we've got to make sure that it matches up here with if we were to put a 1 in here for first term, actually a 0 in here we want, don't we? Let's see. Yeah, ultimately the one in here we want to be negative, I guess. So we want if we put a 1 for the first one, we get we don't want 1 in there. We want 0 because we ultimately get our first term here has to be 1. Keep in mind, so this n would have to be 0 here to make that all 1 right here. Because we'd have to be x to the 0 over 0 factorial. So it'll be 1 over 1, and then putting a 0 in here. If we made this negative 1. Actually, that shouldn't be a plus 1. That's why I got that. I wonder about that. Looks funny to me. That should just be an n. Because by putting a 0 in here, we want this to be 1 also. Because our first term we can see is 1. Okay. And then ultimately, again, just look at the pattern of the tops here. We're going, the powers are going by 2, and the factorials are going by 2's. Okay. Ultimately, we know the general form is just x to the something over something factorial. Okay, those are all even numbers, so we can just simply use 2n for our general term. Okay. If I put a 1 in there, I'd get 2 here, 2 here. If I put a 2 in there, I'd get 4 here, 4 here. Next one would be 6, 6, so on. All right. Now, the next part we got to think about a little bit, because it says here to use this series that we just wrote to write the first 3 non-zero terms and the general term of the Taylor series for f about x equals 0. Okay? So we need to write an equation, or we need to write a power series, Taylor series for f itself, and keep in mind f is that equation up at the top that's piecewise. Okay, and so ultimately, find my right work. I kind of scattered my work all over the place, so let me sort it out here for us. Excuse me. All right. Actually, I think I'll rewrite it just so we got a better look at it. I kind of got it all scattered all over the place here. Alright, so again, we know that we're working with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial and so on. And those are just the regular cosine. And that's it, right? Okay, so and again, keep in mind it says use this to find the Taylor series, the first three for the Taylor series of f, which is above. Now, with f itself, okay, we could do f of 0 because we can see that's negative 1/2. Okay, however, with the others, if we try to take the derivative of that cosine x minus 1 over x squared, we're always going to wind up with an x squared on the bottom, so we're actually going to be able to find any derivatives of that? No. Okay, so that's why we're using this to figure it out. So we're going to manipulate the cosine that we already have. Well, what's going on with the cosine? Okay, it's being, 1 is being subtracted, and then it's being divided by x squared. So if we do that with each of these terms, let's see what happens here. We're going to get 1 minus 1 over x squared. And ultimately that first term is going to give us what? It's going to be 0, isn't it? Now what about the second term? And watch this. I'm going to do this without the signs here. I just want to get the term itself, and then we'll put the signs in there appropriately. So if I do x squared over 2 factorial, which I'll just write as x squared over 2, okay, and I go minus 1, and then I divide that by x squared, that would be my next term. True? Take what I had for cosine, subtract 1, divide by x squared. And if I do that division, I'm going to get x squared over 2 minus 1 times 1 over x squared. And if I distribute here, I'm going to wind up with a half here, and I'm going to wind up with minus 1 over x squared here. Okay. So that would ultimately be my second term, if you will. So that term actually has a value. So again, I'm going to go back to the pluses and minuses and put them together in a minute. But ultimately, we're going to do the same thing here. If I have x to the 4th over 4 factorial, minus 1 divided by x squared, x to the 4th over 4 factorial minus 1 over x squared. And if we multiply this into the parentheses, the x squared and the x to the 4th are going to cancel. And we're going to have our next term be x squared over 4 factorial minus 1 over x squared. Okay. Alright, and then my next term, we're going to have x to the 6th over 6 factorial minus 1. And I'll just skip that intermediate step and multiply by 1 over x squared, so divide. And we're going to get x to the 4th over 6 factorial minus 1 over x squared. Alright, now let's see if we can see what happens here pattern-wise when we add these together, these terms that we've created. So again, this being one term, this being the next term, this being the next term. Okay, so again, the first one was 1, that gave us 0. Okay, the second one was minus this, 1/2 minus 1 over x squared. Okay. The next one was plus. The next term I found was x squared over 4 factorial minus 1 over x squared. And then it was minus x to the 4th over 6 factorial minus 1 over x squared. Okay. All right, and so ultimately, when I do the math on this, I'm going to get negative half. I'm going to get positive 1 over x squared. And when I add it to this one, what's going to happen to the 1 over x squareds? Those are going to be gone. And so we're ultimately just going to get the next term, x to the 2nd over 4 factorial. And then we're going to get minus x to the 4th over 6 factorial. And we'd ultimately have a plus 1 over x squared on the end of this here too. But each time we add a term, what's going to happen to that 1 over x squared? Every time we answer it, every time it's going to get canceled out. So ultimately, remember, we're looking just for the first 3 terms of the polynomial that describes this. Those 1 over x squareds are going to wipe out every time, so we're not going to even consider those. So ultimately, that right there would be our answer for part B. And if you got that part, that's worth 1. And then let's see if we can write the general term here for this. We can see that it's alternating again, so we're going to do that. I'm going to leave that off there for a minute. And we have our x to the, and in this case we can see that the powers are again evens. So if we go to n again, and then what do we notice about the factorials here? keeping in mind that that right there is 2 factorial. So on the bottom we got really, if we want, this is not 2n, because if it was 2n it would just be 2 down here. It would be 2n, we'd have 2 and 2 here. They're not the same as they were in that previous one. So the adjustment we got to make though is that aren't these 2 more than 2n, if you will? So it would be 2n plus 2 factorial. And let's see if that works out for all the terms. And again, keep in mind, whatever we write for this needs to work out. When we put in a 0, we better get negative 1/2. When we put in a 1, we better get x to the 2 over 4 factorial. We can see that that's true. Okay. If we put a 3 in there, we better get a 2 in there, excuse me. If we put a 2 in there, we better get x squared over 6 factorial, which we certainly do. So that part's good. Now, what about the alternating part? This time we want n to be, we want the first term to be negative. Okay. So that means if n is 0, then this would have to be n plus 1, would be a reasonable thing to put there. Okay. 'Cause we want this one to be negative, this one to be positive. If we put a 1 in there, that's going to make this squared. That'll make this term positive, which is what we want. Okay. And just for argument's sake, let's just double check and make sure that it works for that first term. If I put a 0 in here, I get x to the 0, which is 1. I get a negative here. So far I got negative 1 on top, and what do I have on the bottom? If I have 2n plus 2, I'm going to have 2 factorial, which that'd be a negative 1 over 2 factorial. That's exactly what I have here, isn't it? Alright, so general term was worth a point. So far, 3 points for part A. Questions on that one? Okay, let's take a look then next at part B. It says here that f prime, which I've written out the f Taylor polynomial, sorry. So I have the f prime, or the f Taylor polynomial that we just wrote. Okay, and ultimately, remember what the, keep in mind that in this polynomial, okay, the coefficients here are going to be always f of 0. F prime at 0 gave us 0, so that's why there's no x term. F double prime at 0 gives us this coefficient. F triple prime gives us 0 again. F4 prime, okay, fourth derivative, gives us this coefficient, and so on. So keep that in mind. And what they're asking us to do here in part B is, it says use the Taylor series for f about x equals 0, which we just wrote, okay, to determine whether f has a relative maximum, a relative minimum, or neither at x equals 0. Well, the first thing to recognize is how could f even have if f has a relative maximum, minimum, or neither, it must have the derivative equal to 0. Well, how do we know the derivative is equal to 0? The fact that we don't have a what? We don't have an x term. That means the coefficient had to be what? Had to be 0. So that means since f of 0 is equal to 0, f prime at 0 I should say. So since f prime at 0 is equal to 0, we know that we have some kind of flat spot there. It could be a maximum, could be a minimum, could be neither. Now, one thing that we don't have to our advantage is we don't know what's going on to the left and right of f prime at 0. Okay? So we have to think about how else could we tell whether this is a maximum, minimum, or neither. Okay? What does the second derivative tell us about? It tells us about concavity. If we knew the second derivative is positive, wouldn't it be concave up at that spot? Okay? So ultimately it's a second derivative test problem. So if we find the second derivative, keeping in mind that this right here is related to the second derivative. Okay, the second derivative itself is going to be close to this. I'm going to amend this here in just a second. Remember, in general, when we wrote this term, it would have been x squared over 2 factorial. Okay, but ultimately, we have that changed to x squared over 4 factorial. So the question is, what did we multiply that by to get that? Well, 2 factorial to get to 4 factorial, we'd have to multiply it by 3 and 4. So instead of 1 over 4 factorial, this is actually just 1/12 here. Okay. That right there is the second derivative. Because remember, to get this term right here, we would have found the second derivative, okay, and we would have multiplied it by x squared over 2 factorial. Okay? And so ultimately, we were kind of solving for the unknown here, because we know the final product is this. Okay? We know that it had to come from this times f double prime at 0. Okay? So that right there gave us the x squared over 4 factorial that we have. That's why this coefficient right here is 1/12. Because 1/12, 12 on the bottom times 2 factorial is the same as 4 factorial. They both equal 24, don't they? Okay. But one way or another, even if we didn't get that right, even if we had that marked down wrong at the first place, both are positive, which means that the thing's concave up. So we could have still concluded that the point is a minimum. It's concave up in that area. Alright, so concave up, so x of 0 is a relative minimum. And ultimately that was worth 2 points. So 1 for arguing the derivative part here, and then 2 for another point for recognizing that it's a minimum because we're concave up. Okay, questions on part B? Alright, part C, we have to take this g function that they gave us, which is really a totally different equation altogether, and we have to find the 5th degree Taylor polynomial for g about x equals 0. So knowing that, well, we start out with our derivatives here. We start out with g of 0, g prime of 0, g double prime, and so on to build our terms. And I don't know how many we're going to need here, but we'll find out here in just a minute. We know that g of 0 here, we have g right in front of us. If I put a 0 into this function, I'm going to get the area from 0 to 0 of f t dt, which is 0. So ultimately, what is g of 0? That's 1. Okay? So g of 0 is 1, so there's your first term. We know g prime, and I did the work up here. If this is g prime is just f of x. Okay? G prime is the derivative of this, which is 0. The derivative of this area function is the integrand evaluated at the upper limit. So fundamental theorem, part 1 problem. So we know that f prime is just f, or g prime is just f. So if I want g prime at 0, I need f of 0. Well, what do I know about f of 0 in this problem? It's negative 1/2. Why the x? It's the second term. It's got to have an x with it. Okay? So there's 2 terms. Okay? When we do g prime at 0, or g double prime that is, to get that third term, g double prime is equal to f prime. What do we know about f prime at 0? F prime at 0 gave us no term, true? So what's f prime at 0? 0. With that above. So that means there won't be a term here for this one. So g triple prime is the second derivative. Okay? And here's where we have to be a little bit careful here. We know that our second derivative, we know that it's going to have to be attached to x cubed over 3 factorial. Okay? And the question is, what goes here? Well, and again, I forgot to change that again. Ultimately, we calculated that that second derivative was 1/12 in that previous problem, didn't we? Okay. Same reason that we had right here. Okay, we need the second derivative at 0. We just need to figure out what that coefficient is. It's ultimately 1/12. So we'd have 1/12 times x over 3, x cubed over 3 factorial, and that would be our third term. And we need to go 5th degree, so we need probably one more here. Okay. If we try the 4th derivative, that's f triple prime. Okay. From up here, we know f triple prime will give us the non-term, which means that f triple prime is 0. Okay. And then if we want g5, 5th derivative, that would be the 4th derivative of f. And the 4th derivative comes from this. Okay. And again, just like we did above, I'll draw it over here. We know that f4 of 0 times x to the 4th over 4 factorial equals x to the 4th over 6 factorial. So ultimately, what did I multiply the 4 by to get the 6 here? If I already have 4 factorial to get 6 factorial, I just have to multiply by a 5 and a 6, wouldn't I? So ultimately, what would our f prime be? Or f 4th derivative of f would be 1/30th then, wouldn't it? Alright, and so if we get our 1/30th times x to the 5th over 5 factorial, then, let's see, and then where did I do a lot of stuff on here? So anyway, our 3 terms, we already had this one. This one came from our 1/12 times x to the cube, or x cubed, and this is 1/30th. Did I write, which one did I write down wrong? Actually, this would have to be, yeah, it would have to be 30th, wouldn't it? 4 would be 6 and 5, so 30. Yeah, good. All right, so that would ultimately be our last term. And ultimately we could leave it like that. Doesn't really say anything about simplifying it. We can leave it like that and be okay. And the getting the first two right, this was broken down into two parts. If you got the first two right, which were obviously much easier to get these first two right than to get the other two right. You got a point for the first two and then a point for the other two. So 2 points total. Questions on part C? Alright, and part D we had an error situation. And if we, it says use the first three terms to evaluate g of 1. So if we use our polynomial that we just wrote, and we find g of 1, turns out to be 37 over 72. And it says here that we have that our Taylor series is an alternating series with individual terms that decrease in absolute value to 0. And we're going to use the third degree polynomial to calculate g of 1, which we did. And then the next part is explain why the estimate differs from the actual value by less than 1 over 6 factorial. So bottom line here is that if we have this part here, if we have this part, remember what this is the error. Okay, this is our estimate from our Taylor polynomial. This is the actual answer of g of 1. Subtracting those and doing the absolute value is the error. Right? And so the question is, what is the error? Well, remember we've had a couple like this before. One thing that we want to keep in mind is that we know that that error, when we have a Taylor polynomial, okay, up to the third degree, okay, the error can be represented by the next term, the n plus 1th term. That's what I kind of wrote here, so you might want to... Actually, I wrote it down here first. So ultimately, the n plus 1th term evaluated x equals 1 in this case. It's not always x equals 1. It's whatever x is in question here. So the n plus 1th term is the error. Okay? So what was our n plus 1th term? Our n plus 1th term was this. True? And so ultimately the question is that less than that? That's what we want to show. So again, here's the key issue here is that the n plus 1th term evaluated at x equals a, whatever the point in question is, okay, that is the error. Okay? And so therefore, if we find the n plus 1th term, which this is the 5th degree term, right, evaluated at 1, put 1 to the 5th over through 30 times 5 factorial. Okay? That right there, the question is it less than this? And we ultimately know it is, because ultimately this thing right here is 1 over, if I took the 6 out of this and put it with a 5, I'd make 6 factorial here, and I'd have a 5 right there, wouldn't I? Still left over. True? And so therefore, what could be said about this? Is that quantity less than 1 over 6 factorial? Sure. The bottom of this is bigger than the bottom of that, isn't it? 5 times bigger, in fact. So therefore, and that's all we want to show is that that 5th term, that next term, the n plus 1th term here, using a 3rd degree polynomial, our n plus 1th term would be the 5th degree one. Okay, evaluating that at 1, okay, that's always going to be essentially our error. And ultimately we can find that and compare it to what they want us to compare it to, okay, which is this, and show that this is definitely less than this. So like I said, this statement right here is of high importance. Okay? We've had that show up in a couple of our problems where we had that issue where the n plus 1th term is the error, and we just have to compare that to whatever they ask us for, 1 over 6 factorial in this case, and in another case it was a different number altogether. Okay, questions on any part of part D? Point breakdown, if you calculated the estimate, 1 point, and if you showed this part, showed that the error was less than 1 over 6 factorial, that was the 9th point. Questions on anything else on number 6?